In combinatorial games and other similar theoretical situations, it's often useful to find something that stays true no matter what happens. Having something that stays constant or true allows concrete evidence to prove a specific outcome. To illustrate this concept, let's play a simple game. A 3x6 chocolate bar is split along its grid lines by 2 players each turn. The player who cannot split the chocolate bar anymore on their turn loses. Does the player who goes first win or lose? To start, we need to find something that is true no matter what. In this case, we can focus on the number of chocolate pieces there are after each turn. After the first turn, there are 2 chocolate pieces. After the second turn, there are 3 chocolate pieces. After the nth term, there are n plus 1 chocolate pieces. This is what stays true no matter what. Therefore, the player who has the 18th turn loses, since there would be 18 chocolate pieces by then. This means that the first player wins, since the first player goes on odd turns. What we just did in the example before was utilizing something known as a monovariant. Monovariants are quantities that only increase or decrease. The monovariant we had was the fact that the number of chocolate pieces increases by 1 every turn. In general, monovariants are often used to prove some process will eventually end. Additionally, there are also properties known as invariants. Invariants are a quantity or property that don't change during a game or process. Both invariants and monovariants can be extremely useful when proving something to be true. Let's take a look at a simple problem that involves an invariant. A room is initially empty. Every minute, either 2 people enter or 1 person leaves. After 3,000 minutes, could the room contain 301 people? The invariant here is the number of people in the room modulo 3. Every minute, the number of people in the room modulo 3 decreases by 1 no matter what happens. This is a constant value. Therefore, after 3,000 minutes, the number of people in the room must be 0 modulo 3. Since 301 is not 0 modulo 3, we have a contradiction and the room cannot contain 301 people. Here's another problem. The numbers 1 to 100 are written on a blackboard. You choose any 2 numbers A and B, erase them, and replace them with A plus B minus 1. After repeating this process many times, only one number is left. What is this number? Notice that the 2 numbers A and B start with a sum of A plus B and are replaced with a number with value A plus B minus 1. This prompts us to look at the sum of all the numbers on the blackboard. Initially, the sum is 100 times 101 over 2, which equals 5050. Every turn, this total decreases by 1. Since it takes 99 steps to reduce the numbers down to one number, the total would be 5050 minus 99, which is 4951. Since there's one number left, 4951 is the number we are looking for. The problem we just did has other variants as well. For example, A and B could be replaced with AB. In that case, notice that the product of all the numbers on the blackboard will always stay constant. Overall, notice that invariants and monovariants are very useful for problems that have a specific repeating procedure. Both invariants and monovariants can help make proofs for certain problems more rigorous. Thanks for watching.